Hi, everybody, and thank you for joining. My name is Rafael Motafort, and I'm a senior researcher at NREL. Over the past 2 years, I've been working with a team to characterize the portfolio of wind energy software supported by the U.S. Department of Energy. And as part of that work, we're hosting a series of workshops, and today is the last of 5, and it's focusing on the high fidelity modeling group of software. Some of my colleagues from NREL are co-hosting this workshop, and they're listed here. And just a heads up that this workshop is being recorded and the materials will be made available online within a couple of days. I'll go over the agenda here just because it's changed slightly from when the workshop was initially planned. So I'll start with this intro and then an overview of the WETO software stack as a whole. And then after that, model owners from the HFM team will give an overview of ExaWind, OpenTurbine, AMR-Wind, Wind, and ERF. And the update here is that Wind will be discussed implicitly as part of ExaWind rather than having a dedicated section. And finally, and most importantly, we'll have an opportunity for the audience to engage directly with us through polls and an open discussion. And I just want to point out that we're excited for this workshop and the opportunity to have this two-way communication between us, the model owners, and you, the community. So that's why we've allocated such a large amount of time here to the open discussion. As I see it, this really is the purpose of this workshop. We want to hear feedback from you about how the WETO software can be improved, what's working and what isn't, and ultimately how these tools can have the greatest impact in wind energy. So I'll talk about the holistic modeling project and specifically the software portfolio coordination effort there, since that's kind of motivating this workshop. The primary funding mechanism for wind energy research in the U.S. is through the U.S. federal government's Department of Energy, and specifically the Wind Energy Technologies Office, or WETO. So that's the WETO in the WETO stack. WETO's mission is copied here, and I'll just summarize it as WETO invests in wind energy research, development, demonstration, and deployment activities that enable and accelerate the innovations needed to advance wind energy. However, in 2024, what this really means is that WETO invests in wind energy software that enables and accelerates the innovations needed to advance wind energy. The scale of wind energy research supported by WETO is quite large. I'm showing here on the right a list of the active projects only at NREL for the previous year. And the size of the text is relative to the amount of funding. And my point here is just that most of these projects involve the creation or expansion of computational models. And so there's a lot of this happening, a lot of computational model development. Also, I'll point out the WETO project portfolio spans many national labs, and the ones listed here on the bottom have directly contributed to the WETO stack. Now, because of the breadth of this research, there are many software tools, and historically there's been little cohesion or coordination across them. And so the portfolio coordination task of the Holistic Modeling Project is working on addressing this problem. We're in the process of shifting to a new paradigm where our computational models fit better together and and the collection of software moves forward in sync. It's a 3-year project, and in the final year, we're really working on continuing to build the community of users and put a coordinated roadmap into place with a focus on model interoperability. We're also working on an entry guide to the WETO stack, and this is something that was suggested in workshops earlier this year, so it's a direct consequence of these workshops. All of the outputs from this effort are being posted to an online dashboard, and I just want to introduce that briefly. The objective of the dashboard is to provide information on the WETO-supported tools that can enable a given task in wind energy, the state of the included software, the current and future capabilities, and any updates and community-focused materials such as these workshops. So yeah, just kind of clicking through the different key areas of this. Like I said, there's a listing of past workshop material. There's another page has a software listing, and this is meant to be a more expansive list of all of the tools that are actively or in the past have been supported by WETO. There's a page where we analyze metadata that we've been collecting on projects within the WETO stack, and you can kind of filter and tabulate the data in different ways here. And then there's a best practices section. So these are ideas that we've put together on how to improve overall the quality of the WETO stack. I won't go through this in detail, but I just wanted to point out that the areas that we're looking at in these best practices are accessibility, usability, and extendability. And I just wanted to make note of that so that the user community knows that this is an area that we're actively working on addressing within the WETO stack over the coming years. So I hope that sets a little bit of context on this workshop and this idea or this initiative to bring together the tools. And now I'll talk through the different portions of the WETO stack as a whole. So there are a lot of ways we can slice and divide the software in the WETO stack. For these workshops, we've split them based on the technical area in which the software are used. And I'll give a quick description of these categories here. So starting with the TEA and cost models, this group of software allows for estimating the capital costs and operating costs to ultimately determine whether and how to develop a wind energy project. So these are often used early in the life cycle of a wind farm development. Then there's the software for wind farm analysis and controls, and these allow for doing a low fidelity estimate of energy production. After a first sanity check with the TA and cost models, you might use these tools to start working on the schematic design of a wind farm and how it'll integrate into the grid. Next are the mid-fidelity tools for wind turbine and wind farm analysis. These are, in this context, all lumped in the context of, or in the OpenFast category. And that's just because they're mostly within that ecosystem. And with these, you can do a more detailed design of a wind turbine and wind farm. And all of those tools integrate with the systems engineering tools, which are optimization-oriented software with varying levels of fidelity for whole system optimizations of wind turbines. And finally, there's the high fidelity models that enable detailed aerodynamics and structural dynamics that could be used to research or design next generation technologies like farm level flow control or blade treatments for improved aerodynamics. So I hope that gives a broad mapping of where we're going throughout this talk. And so now I'll talk through each of these categories in a bit more detail. Starting with the systems engineering tools, I borrowed this graphic from the Big Adaptive Rotor project, or the BAR project, and I thought it was just an especially nice diagram to show how each of these tools relate to each other in a real workflow. So WISE is this big box in lighter yellow, and it's a powerful design optimization tool. It has a lot of capability, but its core design intent is to enable controls co-design, and that is the coupled optimization of the hardware and the control software of a wind energy system. WISE integrates Wisdom into its design loop, and Wisdom is another optimization tool with lower fidelity models specifically tailored for systems engineering. WISE also couples Wisdom with OpenFast and Rosco, which are two other tools from the WETO stack I'll talk about in a second. And then we can add PyNumad to the mix for higher fidelity detailed design of the composite structural model of the rotor. And then WindSE here on the bottom right isn't yet integrated into this whole loop, but it's a RAN CFD model that's designed specifically to strike a balance between engineering scale models and flow resolved CFD. It's tailored specifically to optimization problems. Next, moving on to the techno-economic analysis and cost modeling tools. I've developed a similar map here. So this diagram shows the tools that are used in different areas of cost modeling in order to ultimately estimate the total value of wind energy assets. So I'll start at the top on the endpoint and then work down. Here, Waves is a software that models capital costs, operating costs, and energy yield to determine a total asset value. It gets the CapEx estimate from either Land BOSSI, Hybrid BOSSI, or Orbit, which calculate the balance of system costs for land, hybrid, or offshore wind power plants. And then Coral is an add-on to the offshore balance of system costs, accounting for shared system installation infrastructure. So like shared boats or shared ports. Waves gets the OpEx estimate, Waves gets the OpEx estimate from Wombat, that's here on the bottom left. And it uses Florist to estimate energy yield. And Florist is in another group of software, but it's still linked here with Waves. And then finally, Narwhal over on the top right is a library of cost equations for offshore wind farms that also integrates with some of the other cost models. So it uses the other cost models to develop the cost equations that are embedded within Narwhal. Going to wind farm controls and analysis, these are mostly related to characterizing and improving the energy yield of a wind farm. Florist is a steady state wind farm wake modeling software. It's very low fidelity, but also cheap to run and highly tunable to existing data. Its core capability is to estimate the energy yield of a wind farm given a set of wind conditions, and this is often used to optimize a wind farm layout or design a wind farm control strategy to mitigate wake losses. Flask, here on the right, connects Florist to field data. It facilitates working with SCADA data to enable wind farm model validation by connecting directly to Florist. It's also used for field experiment design and monitoring field experiments. And then OpenOA here on the bottom is an operational assessment software that provides common data structures and methods for analyzing wind plant operational data to determine wind plant performance. It's a little bit similar to Flask, but it's specifically tailored for this operational assessment data so that the operational assessment data structures are kind of the core, a core characteristic of OpenOA. And it was specifically created to identify various kinds of operational losses. So within the repository, there are examples of using this, of doing this sort of operational loss assessment using open data sets. And then finally on the right, there's Hercules, which is a real-time simulator for wind-based hybrid power plants. It integrates with AMR-Wind, which is a high-fidelity CFD model, to simulate power plants that combine wind and solar power production plus energy storage. And one important component of Hercules is an open source wind hybrid plant controller called WHawk that's also been recently made available. Now getting to the OpenFast collection of tools, there's of course OpenFast along with a set of adjacent tools that enable using OpenFast effectively. OpenFast itself is a multi-physics, multi-fidelity whole turbine simulator for the coupled dynamic response of wind turbines. The OpenFast software contains distinct modules for aerodynamics, hydrodynamics, control and servodynamics, and structural dynamics. And it also supports modeling a variety of turbine architectures, including floating offshore wind turbines. FastFarm, here just noted here on the bottom right, is a superset of OpenFast that contains additional modules that enable full farm modeling, including wind turbine wake interactions. And I'm just pointing out that FastFarm has additional modules, but it includes OpenFast right at the core there. OpenFast also includes its own basic wind turbine controller, but the Roscoe package, which is the reference open source controller, is a full-featured baseline controller and includes a generic tuning process for new wind turbine models. And finally, the OpenFast Toolbox is a Python package that has a large number of utility functions for working with OpenFast and FastFarm. This is essentially just a collection of pre- and post-processing tools that have been useful to us, the researchers at NREL, and so we've been making them available here. And finally, the last group are high-fidelity models that we're discussing more in detail today. I left this slide here just for completeness and consistency with the other workshops, but instead of talking through it, I'll pass the mic to Mike Sprague to introduce the ExaWind program. So Mike, you have to take control of the screen, please.
I am taking control.
Great.
Looks like I've got it. Thanks, Raph, for the introduction. Thanks, everybody, for joining today. My name is Mike Sprague. I'm the PI for the ExaWind project and the High Fidelity Modeling project that has been supporting ExaWind. I'll talk a little bit more about that in a moment. I'm going to go over some of the key high-level aspects of ExaWind, and then I'm going to hand it off to Mark Conry de Frahan, John Rood. I think those are the two who will be following me, and Michael Kuhn will be talking in detail about AMR-Wind. So what is ExaWind? You heard a little bit of this from Raph already. So this is an open source suite of codes really designed for high fidelity, but also mid fidelity modeling and simulation of wind turbines and wind farms. When we talk about ExaWind, we're really talking about the two CFD codes, our physics-based solvers, NALU-Wind and AMR-Wind. But anytime that we're going to be simulating wind turbine in this stack, we need a turbine model, and right now that is OpenFast. Right, that's a key component to the whole stack and running wind turbine simulations. We are now developing OpenTurbine, which is a new turbine simulation code, really designed specifically for our CFD tools. I'll be talking about that as well. We created this software stack really to enable predictive simulations of wind turbines and wind farms, really trying to capture as many of the small scale physics in their interactions with the larger scale physics as possible. Really, it's about creating a tool to understand the wind energy system better and as a foundation for creating, testing, validating next generation engineering models. Key to its development was for it to be performance portable. That's the whole stack. We needed to run very well on more traditional style CPU-based supercomputing systems, but also on GPU-based supercomputers, which are becoming the norm in the Department of Energy's leadership computing system. And importantly, we have GPUs from 3 different vendors now. We have AMD GPUs, NVIDIA, and Intel GPUs. And it's no small thing to make your codes run well on these different types of GPUs. The key capabilities for ExaWind that are in place right now are atmospheric turbulent flow, hybrid RANS LES turbulence modeling, fluid structure interaction, and we have large deformation nonlinear structural dynamics. And of course, that's through OpenTurbine right now, coupled to WETO. Just to show you on the right is an image of one of our recent simulations that Lawrence Chung did on the Frontier supercomputer. This is a hybrid RANS LES simulation of 16 NREL 5 megawatt turbines, where we have full fluid structure interaction, hybrid RANS LES. The tower is there, though it's a little bit hard to see. And this was run on a large part of the Frontier supercomputer over quite a few hours to get these statistically significant results. So that was one of our recent victories with the code. I think there is some confusion out there about the relationship between, well, ExaWind and its underlying CFD solvers, WETO and AMR-Wind. Both WETO and AMR-Wind can be run in standalone mode. If you're running what we call mid-fidelity type actuator line or actuator disk simulations, you might just be running AMR-Wind alone. But if you're going to run high fidelity aerodynamic simulations of a blade section or a blade, that might be WETO alone. But if you're going to be running a geometry resolved simulation of a wind turbine, you would be using the full ExaWind stack, which is WETO and AMR-Wind. And this is a very simple example here showing flow over a sphere. So this is effectively the same approach we use in a turbine simulation. We have some sort of body that we're resolving the flow around, in this case a sphere. The mesh immediately surrounding the body is a WETO unstructured grid mesh, where we resolve the boundary layers and have typically a hybrid RANS LES turbulence model. We have the Tioga library, which provides our overset coupling capability. And WETO is then in turn coupled through the overset meshes to the structured mesh AMR-Wind background solver, which is our large eddy simulation solver. You can read about this. We have a couple of papers. The 2 papers I reference here were led by Ashish Sharma and a bunch of others, and was on the cover of Wind Energy. We are in the process of hopefully publishing a paper on AMR-Wind that describes all of the details of AMR-Wind, very detailed explanation of the theory, implementation, features, our verification, validation, and some of the demonstration simulations therein. So that's under revision right now. Michael Kuhn, Mark H. Henry de Ferhan are leading that effort. Hopefully we will be able to get that published soon. I want to acknowledge the funding and the many developers that have taken part in ExaWind. The funding for ExaWind started in 2016, and that was basically jointly funded between the Wind Energy Technologies Office, who are still funding the project. The Department of Energy's Exascale Computing Project was a large contributor to the code. That's also started in 2016, ended in 2024. We now have new funding under the Department of Energy's Office of Science through the Floating Offshore Wind Energy Earthshot Research Center. That started in 2023, and that will go as a 4-year project. There are other development activities happening out there. I do a quick call out. We have a nice partnership with Total Energies. We're developing capabilities there as well. Status and outreach. So again, I would say we have solid capabilities in place for both high and mid fidelity simulations of wind turbines and wind farms, land-based. We are still doing active development right now. We're trying to improve the performance, robustness of the system. We are developing and coupling to OpenTurbine, and we have implemented two-phase fluid dynamics for floating offshore wind. We're working on validating those capabilities in 2025. If you go to our ExaWind organization page on GitHub, you'll see that we've put up the benchmark repository. This is going to be, this has been going on in this last fiscal year and will be a big activity in the upcoming year. But we have a hierarchy of cases that are relevant to wind energy. So we go from two-dimensional airfoil RANS-based simulations to three-dimensional blade sections to ABL flows to, we have NREL phase 6. We will have the NREL 5 megawatt on there. So we plan to have our meshes, our input files, performance data, outputs, all available on that benchmark website. The idea is to be very transparent and obvious about where we are with our capabilities, how our codes are performing against other state-of-the-art codes and experimental results. And we very much welcome other organizations to, obviously they have full access to all the data and files and so forth, but we would love to have some of our partners push some of their own results to the database, and we can show how we're doing with respect to those other state-of-the-art codes out there. And a quick call out, we do have AMR-Wind user workshops that have been at NWEA for the last 3 years. So if a number of you have probably attended those, but please stay tuned or pay attention to the agenda for the next NWEA workshop, because I suspect we'll have one there as well. I want to say a few words about OpenTurbine. So I talk about OpenFast as being, in this context, a very important part of our ExaWind stack, although it does obviously exist in its own repository and is very much a standalone capability. We are currently creating OpenTurbine. So this is, let me go to the next slide. So OpenTurbine is a flexible multi-body dynamics code. It is very much focused on being a structural dynamics model for wind turbines in CFD codes. We have a very narrow lane of development here. It is currently under development. We have proof of concept capabilities. We've neared completion of all the key libraries for OpenTurbine. I'll talk a little bit more about that in a bit. The development team, Derek Slaughter, Faisal Bouyan, David Dement, Paul Crozier, and myself. Funding for OpenTurbine is coming from the Wind Energy Technologies Office, but we also do have funding from the FlowMass Energy Earthshot Research Center. There are some differences in OpenTurbine from OpenFast. Some of those design choices are listed here. It's C++ with the COCOS abstraction layer. So it is very much designed to enable performance simulations on both CPU and GPU-based systems. It's an index 3 differential algebraic equation formulation. We have a second order Lie group generalized alpha time integrator. The element types in this first round are going to include rigid body elements, geometrically exact beam elements, and constraint member types. We have high order finite elements, very similar to those in BeamDyn. You can track our progress on GitHub under the ExaWind organization, and we have the OpenTurbine repository. Just wanted to share some of the progress and some of our proof of concept studies. We've implemented the IEA 15 megawatt turbine in OpenTurbine. And one of our first test cases was just to do the dynamic simulation of the rotor under fixed RPM and under gravity load, so no fluid dynamics. And we compared OpenTurbine in this proof of concept form with very similar OpenFast models, but in the standard loose coupling form that you find on the repository, and the tight coupling, the new tight coupling version of OpenFast that Derek Slaughter and Jason Yonkman and others are working on. So there's two big takeaways here for OpenTurbine versus OpenFast in these two forms. We can get a much larger time step, stable time step with OpenTurbine compared to both the tight and loose coupling. And the tight, though, is substantially bigger than the loose coupling in OpenFast. Our time to solution is also significantly faster than both of the OpenFast versions. We're very excited about this. We've been pushing very hard on making this as fast as possible. We use sparse direct solvers, for example, and it's all GPU compatible. Though I'll point out that all these comparisons were done on CPUs, and the same CPUs at that. In our second proof of concept study, we coupled OpenTurbine to Aerodyne for BEMT simulations with unsteady aerodynamics, also the Roscoe controller. So we did a case of the 15 megawatt turbine again, where we are simulating a wind gust going from 11 meters per second to 20 meters per second with pitch control active. Some notable things that we couldn't get this to solve in the standard loosely coupled OpenFast version, but the tightly coupled version was able to solve that problem well. OpenTurbine was also able to solve that problem successfully, but we were able to get very fast simulations out of OpenFast, out of OpenTurbine, which was pretty exciting. Let's see. Next steps, we're generalizing our implementation, very much focusing on horizontal axis wind turbines and floating rigid bodies. We're creating an interface for input using the Wind.io turbine definition. We're implementing an application programming interface for fluid structure interaction, focusing again very much on ExaWind, and that will be for NALU-Wind and geometry resolved simulations and AMR-Wind for actuator line simulations. Our goal is to release the production version late summer 2025. And that's all I have, and I will hand it off to Michael Kuhn, who can talk about AMR-Wind.
Hello,
Mike,
everyone.
hopefully you can take control.
All right, I believe I have control now. Is everything looking all right?
Looks good.
Yeah.
Cool. Well, thanks for joining. My name is Michael Kuhn, and I've become one of the main developers of AMR-Wind. And so I'll be sharing more about that code and a little bit in the context of the broader project or category that is ExaWind. So concerning like the inception of AMR-Wind and its roots was in the context of the goal of doing these geometry resolved simulations of turbines, both for land-based and offshore applications. And in that context, AMR-Wind is the far field flow solver. And to do that job well, there are a few requirements. That includes being able to simulate the atmospheric boundary layer and the appropriate setup of the flow, whether that includes taking data from a mesoscale solver or being able to generate a precursor of turbulent flow, atmospheric boundary layer within AMR-Wind itself through a doubly periodic simulation. Also in this context, it's necessary to be able to model turbulence for LES in the bulk of the domain, as well as being able to model interactions with the terrain boundary. And finally, because the scales of the flow vary widely, and we have turbulence in different contexts, once there's actually a turbine in there, one of the key components is being able to have mesh refinement primarily around the turbine itself. So that's kind of where AMR-Wind comes from and where a lot of the development comes from. But because of those capabilities, we have an opportunity as well as a focus to be a useful tool for the whole wind energy research community. And so there ends up being a lot of other applications outside of just geometry resolved simulations. So if this is the general framework of AMR-Wind, where we have turbulent inflow, we have the capability of having a turbine model and also different types of lower boundary models. So on the turbine modeling side, many of these models are coupled with OpenFast. And one of some of the key things that OpenFast provides is the structural modeling as well as the controller. Just there's a lot of research content and usefulness coming from OpenFast there. So on the turbine modeling side, when coupled with NALU-Wind through an overset solver, we have the opportunity to do geometry resolved simulations, but we also have the capability to do actuator line and actuator disk simulations within AMR-Wind without coupling to another solver. And then concerning the lower boundary, most of the time we represent that through a roughness model, but we also have the ability to represent complex terrain and have ocean waves, which are two-phase resolved waves. Phase referring to we actually have liquid and air in the CFD solver. So just some back on the theory and what we're doing physically for the CFD solver. Primarily, most simulations are run as incompressible constant density, and buoyancy is represented through the Boussinesq approximation. We also have available single-phase inelastic and two-phase incompressible. So modeling turbulence in the bulk, primarily we are using a LES framework. We have multiple options for turbulence models there. And then we also have Monin-Obukov representation of the lower boundary. And this is available both in the context of a flat boundary or having complex terrain. There are a few RANS models available as well, but I won't go into detail there. So how does AMR-Wind represent a flow, and what does the domain look like? This is a structured mesh approach. So it's a Cartesian mesh, and it has the ability to perform patch-based refinement through AMR-X, which AMR-Wind is built upon. And how that works in terms of refinement is cells within the domain are tagged, and then refinements are introduced in those areas of the domain. So you can see animation here, where we have adaptive mesh refinement active. Based on quantities in the flow, we can tag cells, which then become finer, and that continues to update as time goes on. So this is something that we can use if we want to track wakes or something like that and have the refinement follow the wake. We also have static mesh refinement available, which is the primary mode of mesh refinement that I would say most users of AMR-Wind are applying. And this is based on geometric sections. Essentially, if you know where you're putting the turbine, you can estimate where you're going to need a finer mesh and apply that. So this is a figure. This isn't the actual mesh, but this represents how you would select regions, tag those, and then AMR-Wind would introduce finer meshes. And we also have a tool which is on the ExaWind organization. If you go to GitHub, but this tool is its own repository. So this is a front-end tool which has both a GUI and a Python interface to set up input files. The input files for AMR-Wind are very simple and direct, but if you're doing a lot of turbines, a lot of refinements, it really helps to have a tool like this. Okay, so I'll go into some more detail about the turbine models. Concerning actuator line, this is linked with OpenFast exclusively at the moment. And in this case, the required mesh resolution depends on the epsilon scale of the turbine model, and it can be a little more restrictive in terms of the time step. But you're actually capturing a lot more than many other models. So it's kind of the best case scenario without resolving the geometry directly. And we have a few things within AMR-Wind which can make this even more effective or more cost effective. We also have actuator disk method, which can be either run with OpenFast or without. So if you're coming to AMR-Wind what do you need to bring to be able to do a study well? You have to start with having target flow conditions. So that can be as simple as a constant flow profile, or you have some type of thermal stratification that you want, or target velocity at the wind turbine. And you can set up a precursor simulation, which will generate an ABL, and that will become the inflow for a turbine simulation. Furthermore, you have to know what type of model you want to use for the turbine. If you are trying to keep it as simple as possible, there are standalone models within AMR-Wind. You also have the opportunity to link with OpenFast and do things with a lot more detail. So there's also the turbulence modeling side of things, where there's a few options that you can choose, and then having sufficient computational resources. Because these are high fidelity codes, they're not the cheapest models out there to run. However, depending on the modeling choices that you take, things can be more or less expensive. We have a walkthrough tutorial on the AMR-Wind documentation, and that can actually be run, albeit a little bit slowly, on a laptop. But in general, most of the research-related work, the high-value simulations, will require significant computational resources. And then what do you actually get from this? So there's a variety of ways to characterize the flow that you get from AMR-Wind. Since it's a CFD solver, we have ways that you can sample the flow and directly get data in a format that you would like to be able to post-process. And then also all of the information that you need from the actual performance of the turbines during the simulation. So I'll just step through with my remaining time what we have out there if you want to understand what does a workflow look like for AMR-Wind. This is directly on the online documentation. And the kind of 3 sections that comprise a typical AMR-Wind workflow. We show how to compile, and we have an actual tool that relies on SPAC to make that as simple as possible for you. And then the precursor step, and then finally a simulation with actuator disks for turbines. So what does compiling look like? It's completely up to you if you want to do it on your own and get the libraries together and just rely on CMake. No problem with that. But also we have a tool called ExaWind Manager, where it makes it very simple. After setting up ExaWind Manager, you set the appropriate environment variables and start it, activate SPAC through it. And then you can choose what version of AMR-Wind you want, the desired options. There's specific features that you want to be compiled into AMR-Wind there, and then install, and it handles everything for you there. And then the first step, kind of low on time, first step is setting up what type of flow you want, performing a precursor simulation, and then the boundary planes of that simulation will be saved. You get something like this, turbulent flow, and then those boundary planes become the inflow planes for a subsequent turbine simulation. So you have all of that valuable high fidelity CFD information coming into your turbine model, and so you can get a good representation of how the turbine will perform. All right, so I'll just mention we have a few things in active development. You can even see these as pull requests, but we have a lot on projects, and those behind AMR-Wind right now. We have a lot pushing toward offshore wind modeling. We also have a new email. If you want to get on our user mailing list, please send an email to us. But in general, pretty much everything can be done through GitHub, and we try to be very active there. So thank you. I'll hand off the mic. All right, so John or Mark gets to take over.
All right, I think it's me now. So I can just take control of this and look at slides.
Yep. There you go.
All right. So I'm going to talk a little bit about, or I'll expand a little bit on ExaWind Manager, which Michael Kuhn talked about. a little bit of information about ExaWind Manager. So it's not only has AMR-Wind and NALU-Wind and ExaWind and all those applications had a lot of development over the years. The way that we build it has also had a lot of effort put into it over the years. So ExaWind Manager is really our fourth iteration of the way that we build this software stack. It's developed mostly by Phil Sakovich from Sandia National Labs, who is not on the project anymore. He's based on all his work on ExaWind Manager, he's moved on. So I also just want to say that what happened to ExaWind Manager really kind of wildly took off into the SPAC world. So Phil made this tool, and then now he's off at Sandia, and I think he's got like $1 million worth of funding to do development on this thing for Sandia to build software there. So this thing is also generalizable beyond ExaWind. So if you buy into the ExaWind Manager, SPAC Manager world, you can still use this stuff in software outside of ExaWind. It's really just a way to build a large software stack or a small software stack. And we have a lot of developer tools on top of it. So also CMake has talked to Phil about doing ExaWind Manager stuff like at Kitware. So I guess I just want to say all that stuff because this project has a lot of weight behind it. So you can see our software stack in this slide and how big it is if you build it with SPAC. SPAC is the supercomputing package manager out of Lawrence Livermore lab, and that's what we build everything on top of. ExaWind Manager is built on top of there. And SPAC is a very international project. All over the world, people use it, not just for HPC even. So our software stack is pretty big. Typically, when we were developing ExaWind, we were developing, about 7 packages at any given time. So we needed a way to really, somebody to develop hyperlinear solvers underneath NALU-Wind and make sure those work well and stuff. So we designed all this infrastructure to be able to facilitate that. So ExaWind's very complex. SPAC was at Packaging Con somewhere in Europe or whatever this last year, and we were at the top of the list for the possible dependencies in a package inside SPAC. And it just even solving ExaWind, the graph for the ExaWind dependency graph is kind of a burden on SPAC. So we're kind of famous in the SPAC world with how much dependencies we have. So we have a complex stack. ExaWind Manager, what it really gives you is the ability to go to any machine that's supported, and we have a configuration for the machine, or we can make a configuration for the machine, and then you don't have to worry about what MPI to choose, what compiler to choose necessarily. You kind of just buy into what we think is the most performant and the most general software environment on the machine. So we also use ExaWind Manager to run the nightly tests. So those kind of happen automatically on a system overnight. And you can run the test yourself in that same type of framework. You can do development. You can just install the software without needing to, you can just go to a machine and install the software without typing in, editing the code all yourself. We have one-line ways to do that, which you can see right here is my single line to build the entire stack. This is what I use most of the time when people ask me, should it work on a certain machine? I just paste this into a terminal on a fresh directory and have it build ExaWind and see if it works. So yeah, I talked about the testing. We test ExaWind, NALU-Wind, and AMR-Wind on machines. We test them with memory checking, with the address sanitizer on in a certain build line. We test them with different compilers, different optimizations. We test them on GPUs. And this all happens in basically a single build line because we just have the environment set up in ExaWind Manager to do it. So I was going to show, if I have a little bit of time, I don't know if I can share my screen quick. Do you think that's going to work?
Yeah, it'll work. You have to stop sharing and then share screen.
So can people see my screen?
Yes.
All right, I'm just going to show you quick. I just did this on my laptop. So expanding on what Michael Kuhn showed, is once you clone ExaWind Manager, and this might be a little busy, I guess, on my screen, but all I have to do is to start it is source this shortcut.sh in the ExaWind Manager directory. I already have my environment set up, so I can activate my environment. Go to the environment directory. I can go to Nalu. I can edit code. So I edited nalu.c right here. And I had previously built the whole stack before. So all I want to do is develop Nalu. And I want to build ExaWind on top of it. So all I do is do spack install once I edited any code that I have, and it will build the whole stack that I have. So it built Nalu, and then it built ExaWind on top of it. And it built that whole thing for me. So I can edit code. We've done this to Hyper. So, you know, we'd want to develop Hyper code underneath this. And all you have to do once you edit the code and you have it set up, you can just do spack install and it will rebuild the whole stack for you automatically. And once you do that, here I'm going to go to an AMR-Wind example. So you can see how I set this thing up. I cloned it. I just started it with the shortcut. I made a directory to put my environment in, and then I did this quick create dev. So this actually clones AMR-Wind for me. And then I can concretize this thing. So spack will solve the dependency graph. And then I make you can just do spack install, but you can also do this dep file, which uses like a makefile situation. And then all you have to do is type make. And this gives you the maximum amount of parallelism. It will parallelize, it will build multiple packages in parallel. It will build those inside of those packages. It will do parallel makes inside of those. So you're really maximizing the amount of parallelism in building the entire environment. And then all I have to do is, you know, I edited code here and did the spack install, and then I can cd, I can do some spack commands to cd to the build directory. And then I can invoke the build environment that AMR-Wind was built in with this. And then I can just, here I run ctest and I just run the unit tests on AMR-Wind. And then all I have to do is iterate on that. So I just took this compound build line. So I can edit code in AMR-Wind, spack install, cd to there, and I can just run this thing over and over again as I'm editing code. And you can do this on a supercomputer too. And this will run the unit test. So that's kind of the short story of ExaWind. I know I don't have a lot of time, so I'm going to give the screen back to Mark Henry DeFron. Sorry, I had to cruise through that stuff.
Hey everybody, let's see if I can take control. Cool, I think that works. This slide. Cool. Yeah, so I want to talk a little bit about how we do performance portability and the programming models. Mike at the beginning here talked about how we support multiple architectures and the landscape has gotten quite complex. So I want to touch base a little bit on what we do for that. Spend just a couple minutes on that. So for NaluWind, we go through the Cocos abstraction layer, which is part of Trilinos out of Sandia. AMR-Wind, we go through the AMR-X abstraction layer. So these are two abstraction layers that gives us performance portability on a bunch of different machines and architectures. We talked a little bit about Tioga. Tioga is currently restricted to CPUs, same for OpenFast. And really our goal is to, you know, effectively use just CPUs and NVIDIA, AMD, and Intel GPUs, right? So that we can minimize the amount of code that we have for all these different architectures. So this is kind of the matrix that shows what kind of software works on what kind of machines, right? All our software works on all the CPUs. AMR-Wind and NaluWind, as I said, is on all the GPUs. NaluWind is currently facing a little bit of setback there for the Intel GPUs, but that should be resolved soon. One thing that's, you know, to tie into what John was saying, this is easily done in the ExaWind manager environment with just a couple different build lines. You just say that you want a GPU environment and it will build it all. And you can build all of these at the same time. So if you want to iterate on developing CPU builds, CPU code and GPU code, and you want all of that in the same environment, that can be easily done with the kind of tooling that John showed earlier. So one of the things I want to flag here, and it's, I think, kind of unique to the way we do things, is that we can, run everything on the GPU, run everything on the CPU, but more interestingly, we can do mixes of these. We can fully pack a node by running, for example, NALUWIND on the CPUs, and then have a couple ranks allocated to AMR-Wind that are handling all the GPUs on that node. So, the way we typically do that is break up the NPI-COM world into a bunch of different sections, and the different solvers will have parts of those nodes, parts of those ranks, and we'll be able to execute on the hardware that we selected. Right, so it's not trivial to do this kind of mixed device mapping. It's kind of unique to the way we do things. One of the reasonings behind enabling this type of flexibility and this type of capability is that it really allows you to fully saturate the node, use, not have any cores idle on the node. Even though you might be leaving a lot of performance on the table by not moving NALUWIND to the GPU, for example, you're still using all the cores and nothing's idle on the node, so you're actually using fewer resources over the course of your simulation. We've done scaling analysis across the whole stack for both AMR-Wind and NALUWIND on GPUs and CPUs. This is on Summit, which was the precursor to Frontier. And really what this gives us is if you change from CPU to GPU, you get basically similar performance, but use a lot less resources and energy over the course of that time. So obviously on CPUs, scaling is pretty trivial. GPUs, as everybody knows, is a whole other can of worms, and our scaling is not ideal there, but we're still very performant on those types of machines, so we are able to use fewer resources. That's all kind of what I wanted to say about our performance models and how we achieve performance on these different machines.
All right, I guess I'm up. Thanks, Mark. So yeah, I'm Elliot Quine. I'm a senior researcher at NREL. I do want to say that this is a multi-lab effort led by Berkeley Lab. It also includes Livermore, Argonne, and Pacific Northwest National Labs. This effort is funded by DOE WETO, as well as the Office of Science. So the Energy Research and Forecasting Model, or ERF, is a regional numerical weather prediction model that provides an essential capability for renewable energy applications. So to support current and future research, and also to inform renewable energy development, there's a need to downscale mesoscale weather to the turbine scale in order to capture more realistic conditions. So you can see an illustration of this on the right that's based on the Grand Challenges graphic. So a modern performant atmospheric model is needed to simulate both larger problems, if you're interested, for example, in hurricanes, as well as to also increase simulation throughput while maintaining accuracy, for example, if you're running ensembles of forecasting ensembles. However, many atmospheric models today, such as WRF, can't use the GPUs that provide most of the computing power on leadership class supercomputers. ERF, on the other hand, is open source and built on top of AMRX, which is the same framework as AMR-Wind. So it's well established, well maintained, provides performance portabilities, and also supports GPUs from all three major vendors. So design choices for ERF have largely been informed by WRF, and our goal is to provide a useful tool both for the wind energy community as well as the greater atmospheric modeling community. So in addition to the existing WRF numerical schemes, we've also developed an elastic solver path that allows us to directly compare to other codes like Pinnacles and CM1. Our methodology differs from WRF in that we use a geometric height coordinate, and we can directly specify stretch grid level heights, unlike WRF, which uses pressure levels or a mass coordinate. As in WRF, grid smoothing is applied over a non-flat mesh, so we can provide a streamlined process for mapping a real terrain to our computational domain, starting from a surface elevation map. In addition, we also provide adaptive mesh refinements and are in the process of developing interface with the DOE global model called E3SM. I also want to hit on the fact that we're developing a code with modern software practices, so we also have continuous integration setup, as John Rood mentioned, or similar to what's being done in AMR-Wind, as John Rood discussed. So just to give a broad overview, this is what an atmospheric model looks like. So if you're simulating a dry atmospheric boundary layer, you might have a surface layer model as represented by Monod-Oblikov similarity theory. But once you start introducing moisture and real conditions, it gets a lot more complicated really quickly. So this is what's implemented in ERF. So everything that we've implemented here has been informed by community needs, as well as a past survey of WRF users that was conducted from another DOE project. In bold is what we've implemented. The other stuff is in progress or planned. I also want to point out that we're trying to leverage external code whenever possible. So the little red asterisk through our interface with E3SM that is providing us the shock PBL turbulence closure or PBL scheme, as well as a microphysics model and our radiation model. I also want to point out that other interfaces are underway. So we're coupling with WaveWatch 3 for wave modeling, and then Remora is a newer project focused on ocean modeling, regional ocean modeling. So our plan is to support a variety of real world, real data simulation workflows. So if we can start with WRF, existing WRF simulation, and use that to drive ERF. We can use legacy WRF preprocessing tools, WPS suite, to generate initial and boundary conditions for ERF. We can run ERF in standalone, and then also use Python tools that we've been developing to drive ERF with either with a variety of large-scale data sets, such as the HER model. And work in progress is offline coupling with the E3SM global model. So now to some results. Here we have just your standalone vanilla, neutral, dry boundary layer. The simulation is configured like WRF, so it uses a 5th and 3rd order advection schemes and also simple turbulence models. And so you get some nice, smooth, turbulent, streaky structures as you would exactly see from a code like WRF. So we've done some validation for neutral cases. The well-established Gables case for stable conditions, we compare well both in LES mode as well as mesoscale mode on the right. I won't go into details for the sake of time. And then next up, we've looked at a convective case with moisture. So we're prescribing, in addition to surface sensible heat fluxes, we're also prescribing latent heat fluxes. We're also prescribing mesoscale tendencies and momenta, temperature, and total mixing ratio for water content. And as with other codes and other work in this field, they've noted that these results are highly sensitive to numerics, especially as we increase our resolution and model fidelity. There's increased sensitivity, and it's a good time to revisit how we compare with other results that were obtained, say, 2 decades ago. But we're pretty happy with these results for this BOMEX case, which was quite challenging. Some examples of complex terrain flow on the left is gravity wave propagation over Wichivangnizi Hill. On the right is flow over the Altamont Pass region. This is a neutral ABL with turbulence triggered purely by the terrain. This is flow going over a hill and then flowing downslope. So adaptive mesh refinements are provided by the AMRX library. Here we have a density current, which is a cold bubble case that we've run in both compressible and inelastic modes with single resolution, as well as adaptive mesh refinement on the potential temperature field. So this basically just says we get the same solution regardless of solver path. Here's an example of a thunderstorm outflow. This demonstrates our particles capability. I think this is really neat because it shows the 2 very different effects of shear and buoyancy. So you can see close to the ground, the part of the initial bubble gets deformed and stretched and then is advected near the surface, whereas the rest of it actually rises up and forms the squall line. So Earth is able to capture quite realistic atmospheric phenomena, and we're quite excited about that. Now moving on to wind turbine modeling capabilities, we have wind farm parameterizations implemented based on the literature, as well as a generalized actuator disk, which is what's in WRF. And on the right is just a simple demo with uniform inflow, but we can certainly run this with turbulent inflow as well. And on the bottom, just to give an idea of sort of the scales that we're modeling, at the mesoscale, we can use a wind farm parameterization where you're aggregating one or more wind turbines into a single flat pancake-like grid cell. We can also run the GAD, the generalized actuator disk. But to get to higher resolution, then we have online coupling with AMR-Wind, which provides access to NALU and OpenFast as well. And we've been working hard on getting the codes to talk together in a native and integrated way. And the final thing I want to hit on is scalability. So we're seeing 5 to 10x GPU speed up when we go from CPU to GPU for typical problem sizes. We scale well both in a strong sense and a weak sense, so we can run to increase the problem throughput, we can run with more and more processors for the fixed problem size. And for about 30,000 cells per rank, we get about 86% parallel efficiency. And then we also scale well in a weak scaling sense in that we can increase the problem size and without increasing our computational time. So we're pretty excited about these results. So the outlook, I think, is bright. We have a paper that details the model and our initial validation effort under submission. Please reach out to me if you're interested in following the project, learning more, and if you'd like to receive a preprint of this paper to get more details into the work that I've discussed today. Our focus area for this upcoming fiscal year, we have 3 big test cases in coordinations with other DOE projects. First is the Tall Towers project, so demonstrating and validating earth and complex terrains with a forest canopy. The offshore environment, we have a case study for a foggy low-level jet off the coast of California. And in extreme weather, we're interested in simulating hurricanes. We're also actively incorporating and partnering with PNNL to incorporate capabilities from Pinnacles into Earth. We're also in the process of implementing other mesoscale to microscale coupling capabilities to expand the type of problems that we can run with data assimilation. And then finally, this is the Office of Science bit. We're working towards quote unquote EarthX, which provides this comprehensive modeling of the marine atmospheric boundary layer environment with wind, waves, and ocean models. And then I have a couple links here to get started. We have documentation that's maintained regularly, and then our GitHub page is also another good starting point. And that's all I got. Thanks, everyone.
Thanks, Elliot. Nicely done. All right, now we'll move on to, well, first I'll say thanks to the audience for just bearing with us through an hour of presentations. I certainly found it informative, so I hope everybody else did too. And now we'll move on to the audience polls. So give me just 1 second, I'll share the instructions for that. Okay, I think we're good. So if we, whoop. All right, so now if these polls will be done through Mentimeter. So if you scan this QR code or go to this website, menti.com. Should be able to, should take you to a page, a website in a browser where you can, you'll see this slide and then we can, yeah, I see that responding is off. So sorry, give me just one sec. There we go. Okay, I'll give everybody just a second to get there. Well, seems like we're going for it. So yeah, the first question is just to get an idea of who we are as a community at this workshop. What is your role in the wind energy industry? A lot of researchers. Just for, it seems like maybe we all get it, but this engineer technology developer was meant to be just distinct from a researcher. So maybe you're an engineer in industry or working on some specific technology, but not, you're working on the development or maturity of that technology. Okay, so yeah, definitely strongly research oriented, which I think was expected, but some engineers. Okay, good to know. Similarly, that same style of question, but as it applies to HFM software, what type of user are you? Practitioner are people who run the codes. Developers are people who extend it. And of course, as a developer, you're going to run it. But that's distinct from practitioner in that you're probably not doing a wind energy analysis with it. You're running it just to test what you've done. And then program managers might lead projects where their colleagues within the program would use these codes, but they themselves don't. Can choose multiple, which I think many of us are probably multiple. Okay, yeah, I think this is as expected as well. It's about half and half, or split equally on practitioner and developer. So that's good to know. Yeah, a lot of strong user base here. Next, what type of computing platforms are critical to you? So we've got workstation and HPC and CPU and GPU. And here we're really trying to understand, like, basically what should we be supporting here? Yeah, like what are the real needs of the community? Strong CPU and GPU on HPC. Okay, good to know. Yeah, I think this is a little more of a surprise to me. So that's good to know that. I mean, I guess, of course, these tools are obviously tailored to leverage GPUs. So maybe this community is self-selecting on that. But that, yeah, this does inform our view, I think. And regarding support and engagement from with the developer teams, how have you successfully gotten support in the past? So this could be user support, developer support, just asking questions on the future state of these tools. What has worked in the past? And just so you know, looking ahead, the next question is going to be, how do you prefer to get user support? So this one is specifically what has worked. Okay, GitHub, software documentation are the clear leaders. Seems like a lot of outreach directly to the researchers here, so that's also good. Okay, good to know. Yeah, this is really nice to know. Yeah, like I said, the next question is, how do you prefer to get support in the future? So the options I've listed here are somewhat generic. Current status quo is good, hands-on workshops, direct access to researchers, and then we don't have any paid support options, but if that's something that is a strong need or strong interest, we can look into that. Sorry, it's not that we don't have any paid support options. It's just that they're not as well developed. So sorry for the miscommunication. All right, so strong preference here, I think, for the hands-on workshops and the status quo. Yeah, I think I probably fall into that camp as well myself. So that's good to know and nice to see that reflected. And we can keep that in mind as we plan our ongoing work. For direct access to researchers, it's good to know that's a strong second, and we can think about how to make ourselves more available in a sustainable way in that regard. I actually want to go to this question. I wasn't sure if I was going to bring it up, but I'm curious if I'm curious what hasn't worked in the past. So this is just looking back at the one that we previously asked, what has successfully worked? Is there anything specifically that you have tried, but that just doesn't seem to work? This could be things like you email a researcher and you don't get a response for months, or you put something on GitHub and it just kind of goes unnoticed or falls through the cracks. And the reason I'm asking for this is I'm just curious what, like, us as researchers, what we're not seeing regarding the user community and the user needs. Software documentation has not worked. It's good to know. Yeah, it seems like the clear thing that could maybe use more attention is the docs, with some close seconds on the examples and GitHub issues and discussions. Okay, that's really nice. On this particular note, if anybody has anything else to add when we go into the open discussion, that would be interesting to know. Any kind of clarification? Okay, now I'll just go back. This is not a multiple choice, it's a word cloud. So what workflow capabilities are missing in the HFM software? And of course, don't write sentences, but 2 to 3 words or some small number of words to describe what specifically workflow capabilities are missing. Meshing. Okay, Cloud HPC. Okay, good to know. So generally, maybe pre and post processing, the Cloud HPC support. That's a good suggestion. Model details. I wonder if that is regarding the mathematical models or the yeah, like basically the settings and configuration. We got solid shell elements, mathematical. Okay, yeah. Mesh geometry. Okay, so it seems like it's kind of converging on meshing, pre and post processing, and then essentially, in my mind, details on models goes back to the documentation. Yeah, and then somebody listed documentation. So yeah. Okay, I think there's some clear categories here. Yeah, somebody reiterating documentation. Good to know. The next word cloud input, and this is the last poll question, are what modeling capabilities or physics models are missing in the HFM software? So not so much workflows, but regarding the math or physics models embedded in them, is there anything that you see clearly missing? Fair. Validation. Some validation on the validation being missing. A few people have responded with the same. Linus-Boltzmann method, numerical dissipation. Okay. Okay, it seems this is trailed out, and yeah, thanks a lot for the input. This is really good to know, boundary conditions. I hope that this gives us something to kind of start the discussion on the open discussion. So especially on this slide, if any of the presenters have any clarifying things to add here, we can start with that in the open discussion. So consider this the open discussion now. For the AMR-Wind or ERF teams, do you have any comments on the meshing suggestion on the missing capabilities?
More of a clarifying question. Like the majority of what we've talked about today has been the structured codes, and so the meshing there is sort of a different concept. So I'm wondering if that is talking about mesh refinements for those codes, or if it's specifically talking about geometry resolved simulations, like through WETO. Or maybe a third option.
I don't see any comments in the chat. Yeah, if anybody has any clarifying comments on that, feel free to raise your hand and call on you to answer that. How is the blade resolve meshing handled?
We don't have a specific tool that we provide. You have to use a separate meshing tool. Mm-hmm. So most of the researchers rely on pointwise.
Yeah.
But yeah, there's not a lot of open source options when it comes to meshing anyways. Mm-hmm. So that's kind of its own expertise.
Yeah. Okay, so you bring your own mesh.
But I guess there could definitely be more documentation on that side to inform users about what to do or best practices. But I don't think we'll begin to support a meshing tool through any of our projects.
Yeah, currently in ERF, the only manual meshing that somebody might want to do that I can imagine is if you want to manipulate the terrain geometry in some way. So for instance, if you're trying to simulate a real terrain, but you're trying to spin up turbulence, then you might want to go in and smooth the edges of your domain to a flat boundary so that you can recycle the float. But yeah, everything is pretty automated and streamlined. You just pick a smoothing option, and then it makes sure that you don't have. It just guarantees that you have a well-formed mesh above the surface.
Okay. So the AMR-X component of this, that's the structured grid. Does that kind of make its own mesh?
I would say so, yeah. Basically, you're specifying the size of the domain and the number of cells in each direction. So there's always a base level mesh. And then any additional complexity comes from choosing refinement regions or a refinement strategy.
Okay. All right, good to know. Similarly to the model owners, what would you say to the point that validation is missing? Do you agree with that? Do you think, yeah, what's your opinions on this?
I think this can mean a couple of things. I think people might be concerned with validation at scale, which is difficult depending on the way where you can actually find data for a whole turbine and turbulent flow. But we did mention that both for AMR-Wind and ERF, we have publications that are pending. And I think both of those are going to heavily address validation questions. So hopefully that is, we're in the process of meeting that request. But yeah, it's definitely a big concern to have unknown validation.
Yeah, for ERF, we'll fully acknowledge that up until now, we've been focused on just writing code, building the dynamical core, making sure everything is robust and working properly. So more on the verification side, but we're definitely very excited to be moving into a validation phase this fiscal year. And so, yeah, that's why we're targeting those three separate field campaigns that were conducted, and we're coordinating with other DOE projects on that front to share data and share model inputs and outputs.
Is the AMR-Wind database that was mentioned, I think Mike said that was specific to wind energy cases?
That's true. Yeah, that's meant to be a place where you can come and see how to run cases of interest and have the results easily documented there. A benchmarks repository.
Okay. Are any of the validation cases are those going to serve as validation cases, or is that really like a performance more of a verification benchmark?
I think it's both. I think we're trying to address both.
Gotcha. Okay. All right. It's like we've got a question here.
Hi everyone. Yeah, I have another kind of.
Hi Benito.
Yeah. Currently, do AMR-Wind and also NanoWind support simulation of floating offshore farms? And if so, what are the differences between the bottom fixed simulations, also with interaction or with OpenFast?
Yeah, so that's a great question. That is the focus of our research this year. So that's not really it's not a complete feature at the moment. We have the ability to simulate waves, but to couple that with an actual floating substructure and to couple that with an OS model, that's not yet available.
Okay.
So,
thanks.
but you can run simulations of an ABL with waves present in the domain and have a actuator-based turbine, but the representation of the substructure in OpenFast wouldn't be coupled with the fluid.
Okay.
Michael, can you also add, please, maybe once the feature is implemented, what would be the difference of modeling in the ExaWind suite versus OpenFast in terms of levels of fidelity and what equations are solved?
Right. I mean, I am not familiar enough with Subdyne as a module of OpenFast to go into detail, but our goal is to actually have a geometry resolved semi-submersible structure floating, moored, interacting with waves, and then we'll be able to add a turbine to that. So that is more along the lines of what Star CCM can do, and not necessarily what OpenFast can do.
Okay. So yeah, the wind turbine platform they fix in the AMR-Wind simulation.
You might need to repeat that. Are you asking if the
About the
turbine would have to be fixed? So
I mean, also if I couple AMR-Wind with OpenFast, okay, for floating offshore wind turbines, yeah, in AMR-Wind the turbine base, will move or not.
So OpenFast is going to compute all of the motions of the turbine. So depending on what you do to set that up for OpenFast, OpenFast will compute how the points that represent the turbine move within their wind domain. So that you have access to the functionality of OpenFast directly, but that functionality will not be coupled to what's going on in AMR-Wind, except through the direct aerodynamic coupling at the blades.
Okay.
So that OpenFast model won't receive information from AMR-Wind except the velocities at the blades, but you could have additional stuff going on the OpenFast side.
Okay, thanks. So maybe you suggest a couple of simulation maybe between fast farm and AMR-Wind. So an AMR-Wind, a precursor simulation AMR-Wind, and then a fast farm simulation for floating wind turbines.
I'm confident that's available, and I know some researchers that are doing it. Yeah.
Okay, thanks.
Thanks for the question. Just as a clarifying point, Michael, they're coupling ExaWind with multiple instances of OpenFast turbine models, or coupling ExaWind directly with FastFarm?
That's a good question. I don't know that I want to answer that confidently.
Sure.
That's not my work.
Yeah, maybe a detail anyway.
I can answer that one. I'm not on the panel here, but yes, we typically use like AMR-Wind as a precursor for FastFarm to generate the flow field. And then, of course, FastFarm can do multiple floating turbines if that's what the question is. But yeah, we usually as a precursor, not as a coupled tool.
Right. Okay. Okay, thanks, Jason.
There's also a question in the chat about twin turbines, which I think probably means two wind turbines off of the same support structure, either the tower or a base offshore. I know this is a capability that's in process in OpenFast in development. Jason, you can correct me if I'm wrong, but yeah, in ExaWind, do you see any barriers there?
So the ability to have a floating platform in ExaWind, geometry resolved, that is under development. But the pathway would be different than what is being looked at on the OpenFast side, because for doing it in a geometry resolved sense, it would be on the user to be able to generate a mesh for that. And once the mesh is created, then it can be simulated. So I don't think that in particular would require a much significantly different pathway than an individual turbine in the geometry resolved category. But if you're looking at using a different type of model, then we won't have it available any faster than OpenFast will.
I was just thinking about these other questions here. This one was a little bit of a surprise to me. I think I expected the workstation CPU and GPU to be higher. Though maybe given that most of the audience here are researchers, we all do have access to DOE or other fancy HPCs. Yeah, I don't know. Was this a surprise to anybody else, any of the other presenters?
I think what you said about self-selecting is correct. I think that's kind of what we target, at least in the ExaWind stacks. We're really focused on HPC.
Yep.
And you really want to be using those LES codes at HPC. So I think that makes sense to me.
What is the practicality of ERF and or ExaWind on workstation use? Is that more just for kind of like developing your processing your toy problem before going to HPC, or is there a practical use case on workstation?
That's typically how I've seen it done. Is develop your case, you develop your code either on CPUs or GPUs on workstation.
Yeah.
But then you push that to CPU or GPU on HPC.
For ERF, I think, yeah, that, and also, we can run ERF in a single column mode, depending on your region of interest. If you're just using the mesoscale model and a PBL scheme, and you're not downscaling to the turbulence resolving scale, then I think it's possible that that a problem of interest could fit on a workstation. Actually, fun fact, the terrain simulation I shared over Altamont Pass, that was run on my laptop for a day and a half when our HPC cluster went down. So it's certainly possible. It just becomes kind of a creative challenge to tailor your problem to fit on your workstation. I think this is interesting that there are 18 responses from people that would like to run on a workstation. So I think it's something for us to keep in mind.
That's a good point.
I think the other thing it emphasizes is the degree to which people want to be able to go back and forth between CPU and GPU and not have, that's what I'm seeing is the real mix. And again, coming back to the workstation question, it really depends on your laptop or your workstation. The newer the model, potentially the more powerful. And so you can do a lot. I would say it's absolutely a good platform for development, but as Elliot pointed out, you can run real simulations if your workstation's powerful enough.
Mm-hmm.
And I think that's a very reasonable mode. As Elliot pointed out, there's a lot of investigation you can do at the smaller scale. So not everything needs to fill frontier. Mm-hmm. And I think that all of the codes we talked about target the whole range, from the laptop to the full machine.
Yeah.
Yeah, it's an interesting thought experiment that our laptops today would blow a supercomputer out of the water from 10, 20 years ago.
Yeah. That's a good point, and that the distribution, of course the HPC with GPU is much higher, but there is a relatively flat distribution, not considering that. So this does kind of just point to the need or desire for portability.
Right. You don't want to have to maintain 3 different codes. You know, oh, I've got my laptop version, I've got my supercomputer version. It's really a compile time option, not a code change.
Yeah. Yeah. Okay. Yeah. Good point. Let's see. The other thing I wanted to bring up was whether any of the teams saw any insights from anything interesting from these responses. I feel like from my work, this is kind of how I expected it, but this is what has worked. And then what has worked.
Another sort of a follow-on question. So I don't know if the audience, hopefully the audience can participate a bit here. For unsuccessful use of the documentation, I'm wondering if that is referring to the, you wanted more details on something and it wasn't there, or the details you found were wrong because they were out of date. Just curious if that's, if that response falls into either category more significantly.
Good point. I guess I'm also curious why there were 11 people that said that examples weren't helpful.
Yeah, in past workshops, the feedback we've gotten is that the examples can oftentimes be out of date, just like Michael's referring or kind of getting at, or that they are almost too trivial. So it'll show you how to get, it's kind of easy to either write in documentation how to get started or show an example, but how to do something of actual value can be more challenging in an example. And that's what I've heard, that it's harder to find the examples that show you that. Like, I want to do this study. How do I do it? But I think that's also just part of the challenge of open source software.
Yeah, you can't create an example of everything.
Yeah, exactly. I don't think this is what Shreyas was responding to. I think he wrote in the chat whether the responses contain, or sorry, that whether this contains responses from the ExaWind and ERF teams, but I know I answered these questions, so I assume these also contain our own responses. So maybe that's another thing that's just good to know.
Yeah, I was just curious, I would obviously expect HPC and GPU to, CPU and GPU use case to win out, especially on the DOE funded activities team, because we have access to Frontier, Kestrel. I was just curious, what other resources are other people using, tapping into, and
Yeah, actually, if we do subtract at least the presenters, this is almost flat.
Raph, where do you think cloud is in here?
Yeah, that was one of the suggestions here.
I saw
cloud
that.
HPC support, and I didn't think to include that here, but it's a good question. Do you have a sense, Anne, or anybody else?
No, I'm curious if you take Shreyas' suggestion, subtract out the developers of these software, and ask the rest of the participants, is anybody primarily interested in cloud computing?
so is there an opportunity to add one more question on that?
Sure.
Yeah, so in-prem HPC versus cloud, right? That would be one question.
What's the opposite of cloud?
In-prem, on-prem, or
Okay.
in-house, right? So the
in-house in a very loose sense.
Yeah, they call it on-premise for some reason, but it's basically, you maintain the entire infrastructure.
Okay.
Although that is kind of loose these days because you might have a fully controlled cluster, but it's hosted in a data center. Our AWS also hosts that stuff. So what it really means is, are you getting nodes on demand versus do you have this dedicated resource always sitting there?
Right.
Oh, can you also add a GPU option on this one, if you don't mind, Rap? I'm just curious.
Well, cloud could be GPU. So
Yeah.
you want to say cloud-based non-GPU and cloud-based GPU?
Yeah, because in the previous one, you had
yeah,
HPC CPU, and then there was HPC CPU plus GPU.
Yeah, okay.
Really putting you on the spot, Raf.
Yeah, when people watch you type. Yeah, I guess the problem, maybe the issue here is, I don't know, we don't have, I think, too many people have dropped off. That's what I mean to say. But yeah, we can try to take this poll. So it's still live.
I
so
don't
if you
see
go
it
to this
showing up
website-
on Mentimeter yet. Still see the HFM software missing.
Oh, because I need to present it. Okay. All right. How about now? Oh, yeah. This is what happens when you do things live. This last one can be CPU and GPU. Yeah, it's too bad we didn't have this at the start. I think it's a good point, and certainly something that I'll keep in mind for future polls. So just to update on the chat, John Rood is pointing out that the last time ExaWind was tested on cloud resources, it was 6 times slower than Eagle.
So did that have dedicated InfiniBand backing on and all through and made sure that all the nodes were on the same rack? John, do you know?
Yep. Yeah, it was on Azure. So I haven't done AWS, but we did it on Azure, which gives us like, yeah, a contiguous set. It also had Luster on it. And yeah, I thought it was going to be better, but it was not great. We used the MPI that they gave us too.
Okay. So one thing I had noticed was that not only so they might give you a group of cloud nodes, but you have to make sure that they are in the same placement group. Otherwise, to your point, the performance just drops. So there is a lot of manual node selection you have to do to submit jobs. So I was just curious if
yeah, maybe I wasn't too diligent about it, but it would create the cluster for us. Like as soon as we logged on, it would take like 15 minutes for it to provision.
Yeah.
So
I had to do like a Slurm constraints features where I select particular named nodes so that they fall on the same rack. Otherwise, to your point, performance will just drop like a rock.
Yeah. Okay.
I also wanted to just circle back from the chat on the question of Michael's clarifying question on documentation. Somebody responded that for AMR-Wind, at least the issue is the lack of documentation, and lack of detail in the existing documentation. Yeah, so maybe that just clarifies that suggestion
Yeah,
here.
that definitely helps some. It just makes me a little more curious though, because whether that's like the theory side or the user side, and I feel like we tend to devote our efforts on the documentation front to user information and not theory. And I hope that assuming when we have a published AMR-Wind paper, a lot of the theory questions will be there. But yeah, thanks for bringing that up.
Okay, well, we're at a little bit over the time that I had initially scheduled anyway. So we'll call this discussion here. And I just wanted to finish with just thanking everybody for coming. Yeah, like I said at the beginning, I think this is a really important opportunity for us as model owners and for the group managing the WETO Stack to have the opportunity to have input from the community and have these discussions. So if you have any feedback on this workshop, please send it to me directly. My email address is here. And we intend to do these types of workshops on an ongoing basis. So improving them as we go and making it more useful for the user community would be really nice. I'll also send a feedback form in the next couple of days that allows an opportunity for anonymous feedback. So if you don't want to follow up, then you can send anonymous feedback and tell me your real thoughts. And then these are the links for software repositories, for these software repositories of the models we discussed, as well as the WETO Stack site. But I'll include all of that in the follow-up email, as well as I'll point out the link to this workshop recording and the slides from this workshop. That'll all be on this site. So with that, thank you very much for joining. And yeah, thank you for your time. Thanks to all the presenters for the hard work.
Thanks, Raphael.
Thanks, Raph. Thanks, everyone.
Thanks, Raph. Thanks, attendees.